Welcome back. Let's talk about norms, distances, and similarities. A norm is any function that measures the magnitude or length of a vector. It's typically written with this notation with 2 bars on either side of the vector. There are actually more than one way to measure the magnitude of a vector, but the most common way is the Euclidean norm. It's also known as the 2 norm and written with a 2 on the outside of these bars. It's actually so common that we often don't even include the 2 here. It's just assumed that the norm of x is the 2 norm. And what you should recognize here is the distance formula. If you ever took undergraduate calculus, it'd be the distance of any point in n-dimensional space from the origin. It's the sum of squared elements in that vector, the square root sum of squared elements. Another way to write this is that it's the square root of x transpose x. Again, when I take the inner product of a vector with itself, I get the sum of squared elements. If you don't see this right away, I encourage you to write out an example and convince yourself of it. The distance between 2 points, say x and y, is the norm of their difference. So it's the norm of x minus y. And we can use this information to determine which points are more similar to each other. We may even choose to create a distance matrix, D, which contains the pairwise distances between points or observations. So the ijth element of D would be the distance between observation I and observation J. This would be what's called a symmetric matrix because the ijth element would be the same as the jith element. So it would have that symmetry around the main diagonal. I can try to give you a little tiny example of why this might be useful. Here I have some data about students' GPAs and their GRE calculations. And I have just call them labels on the observations A through E. I can create a distance matrix that tells me how far apart each observation is from each other. So from this matrix, you can see that A and B have a distance of 1, whereas A and E have a distance of 4. That's consistent with what we see in this picture. A and B are much closer than A and E. You can also see that the main diagonal of this matrix, which of course contains the II elements, same row, same column, is all 0. That's because a point is the distance between a point and itself will always be 0. You can also see the symmetry. I like to call this fold over symmetry because I remember kindergarten or first grade when we talked about fold over symmetry, and it's fold over symmetry along the main diagonal. That's what we refer to as a symmetric matrix. And that's because the distance between point E and B will always be the same as the distance between point B and E. Distance is a symmetric measurement. And distances can help us find groups of similar objects or clusters. So here in this matrix, if I kind of partition it, you'll see that I have a group of objects up here that are close to one another, a group of objects down here that are close to one another, and those correspond with groups of objects that seem to be clusters in my data. Now, this was not an example of how clustering is done. Of course, a distance matrix would not be in order according to the clusters, and it would not be just as easy as drawing lines to separate the distance matrix. I'm just trying to give you a sense of what a distance matrix is and how it might be useful to us. Other norms that exist are the 1 norm and the infinity norm. These are probably the more commonly used norms outside of the 2 norm. but they're still not very common. The one norm is often called Manhattan city block or taxi cab distance. It's the sum of the absolute values of the entries in the vector. And it's called the city block distance because if you think about getting from point A to point B in the city, you have to move along streets. And so this would count the number of blocks that you traverse on the most direct path to from point A to point B. The infinity norm, also known as the max distance, is just the maximum value, maximum absolute value of the entries in the vector. We'll talk further on, and there are some examples on the worksheet that ask you to interpret these distances and maybe give you a sense of why you might pick one over the 2 norm. Although, in all honesty, you won't often do that. You might just play around with it and try things, though. There are also some norms that show up in statistics. The standard deviation, the formula for standard deviation is as follows. Now, when I got to graduate mathematics and we learned the definition of norm, and then I got to graduate statistics, it made me very happy to rewrite all these yucky statistics formulas in very clean mathematical notation. And one of the ways that that's done is by having a line at the beginning of every statistics textbook that says, throughout this textbook, we're going to let our data be centered. What we mean by centered data is that every observation, we've subtracted the mean. And so once we've done that, if this is a vector of centered data, meaning the mean is assumed to be subtracted from every element, here I just have the square root sum of squares. Well, that's the 2 norm. So the standard deviation is a 2 norm. The correlation coefficient is this absolutely hideous equation, and it becomes very clean in linear algebra. It's just x transpose y over norm x norm y. Again, as vectors of centered data where we subtract the mean. The next video, we're going to take a leap into the world of statistics and talk about the multivariate normal distribution.